Hello and welcome to the Minnesota Stormwater Seminar Series. It is my privilege to introduce the seminar series today and our speakers. The seminar series is brought to you by the St. Anthony Falls Laboratory in partnership with the Water Resources Center and the Minnesota Pollution Control Agency. The seminar series is funded in part by the Minnesota Stormwater Research Council, the Minnesota Clean Water Land and Legacy Amendment, with support through the Clean Water Council and members of the Minnesota Stormwater Research Council. A few logistics and announcements for today. First of all, our schedule for today is a presentation on our topic for about 40 minutes, following 40 minutes of Q&A with a panel discussion. As a reminder, for those of you joining us online, we will entertain questions to our speakers and our panelists using the Q&A function of Zoom, not the chat function. And we will also have questions here in the room, and I'll have to pass the mic around so everyone hears that. As a reminder, all of our seminars are recorded for your viewing privilege after in the months ahead. And speaking of months ahead, join us December 14th as we continue our seminar series and into 2024. A reminder for some of you that following our seminar today and panel discussion ending at 3 p.m., we will have a focus group about assessing the stormwater research needs for Minnesota. This is one of 4 focus groups that we've been having this week. We invite you to participate here in the room or online. But just a caveat that we have a separate Zoom link for that focus group, and we will put that in the chat for those of you that are online. For any information about our stormwater research needs assessment, please visit our website that is on the screen and in the chat function. Now on to today's seminar. This month's seminar is titled Harnessing Minnesota Stormwater Data for Improved Modeling and Management of Water Quality in Cities. We will again start with a keynote presentation by 2 of our principal investigators, and just thought that this project is one of the many funded by the Minnesota Stormwater Research Council and recently completed by our 2 PIs. Our first presenter is Jacques Finlay, a professor from the Department of Ecology, Evolution, and Behavior here at the University of Minnesota. His group does research in wetlands, lakes, ponds, rivers, examining both global and local changes in freshwater systems. He's an investigator with the new NSF-supported long-term ecological research site here in the Twin Cities. He's joined by Ben Janke, a research associate here at St. Anthony Falls Laboratory, working with the Department of Civil Engineering, Civil, Environmental, and Geoengineering, and also with the Department of Ecology, Evolution, and Behavior. He is also affiliated with the Natural Capital Project at the Institute of the Environment here at the University of Minnesota, and his research includes broadly aspects of urban eco-hydrology with a focus on stormwater management. So welcome, Jacques and Ben.
Thanks so much, John and Andy. I'll start off right away thanking you both very much for everything that you do. Introducing the rest of our team here, Mike Trojan, who's in the audience today, Minnesota Pollution Control, now retired mostly, Mary Merrick Sparts, UMN, and also affiliated with the university, the new LTER that John mentioned. So starting out with this project, which assembled, organized, analyzed stormwater data collected by many of you out there. Many people involved in this, but no one more responsible. If we can point to a singular heroic figure, it's Ben Janke here. So I'm delighted to co-present with him today on this. And I can't make the font big enough here to express thanks, and I won't read through this long list of people that we need to thank, and organizations. So the data for this project came from data that was collected by many people, many organizations, and thank you to those organizations. Thank you to those individuals who took the time to answer questions patiently and hung with us on that. And thank you also to a couple of University of Minnesota students, Amanda Van Pelt now in graduate school with in North Carolina, and Katie Hoffman also now in graduate school. So big thanks to many of you, and big thanks to the Stormwater Research Council for funding this research, right? So it's a tough sell to ask for money to work with data that's already been collected, right? So we did that, and you funded us. And I'm going to show you just a little bit, and we are going to show you just a little bit of sort of what we found and what that looked like. So I don't need to remind all of you while we're here, right? Urban water resources are disproportionately valuable to many people. This is a picture of Como Lake, which I'll start and end the talk on. It is a site that's visited by thousands of people every day, and it is heavily impacted by stormwater, right? You can't see all of the pipes sticking into it, but there are a lot of them, and it's a big challenge, and a challenge that's worsening with effects of climate change, increasing precipitation intensity and temperature, just to name a couple of effects. So the motivations for this project were better understanding of stormwater. And the starting point description here, this diagram indicates just some of the complexity, some of the sources that contribute to stormwater pollutants, right? But this doesn't represent by any means all of them, or of the complexity, the seasonal, the spatial variation in these pollutant sources that is baked into the urban environment, right? So there's a lot of complexity out there, and we need more information to grapple with it, to deal with it. So really briefly, the motivations for this project were sort of acknowledging that urban ecosystems are really complicated. Management of them depends on the context, the setting, the understanding of relationships within diverse urban areas. We need more data to do this. If we increase our access and use of data, we're going to be better off, right? We're going to make better decisions, target pollutants more effectively, and have better outcomes in a future that is changing, really is likely to change in the future, right? So this is a slide that I made yesterday, so it is definitely half-baked, but it's trying to represent just some of what we tried to do. Sort of the vision for this project, right, was to capture diverse data collections by Minnesotans in cities, bring that together in a database, and then sort of have a better uses, diverse products and outcomes from bringing this data together. So we'll try to convince you of the value of putting this information together, learning from it, and going forward from there. So with that, I will pass it to my co-conspirator here in this talk, Dr. Ben Janke. And I will remember to turn off the microphone.
All right, thanks. So this is just a quick outline of what we're going to go over today. I'm going to kind of scoot through the methods pretty quickly so we can get to the fun stuff. And we have a couple of case studies to kind of provide an example of how we were using this data set on a couple familiar, maybe unfamiliar topics here. So first and foremost, as Jacques said, one of the motivations for this project is that there is no central repository or clearinghouse for stormwater data in the state of Minnesota like there is kind of for lake and stream data. And so to gather all this data together, we had to reach out to people, where we knew there were data sets, where we knew there were, past reports, online information. We made contacts across lots of organizations and cities, and we heard back from a lot of people, primarily in the Twin Cities metro. And we ended up with maybe 200 sites or more than that in our first kind of swing at this. And right off the bat, we were kind of encountered some obstacles that really slowed us down a little bit in this project. And first of all, there's just an enormous amount of data out there. So kudos to all of you who are doing this work. You just blew us away. And that meant that data was coming in all shapes and sizes and formats. And that created a lot of work. And for me, that was a bulk of what I did in the first probably 2 years of this project, was just organizing, cleaning, and formatting data. There's also a lot of monitoring that's been going on in the last 2 years. So we're kind of incomplete with respect to the last 2 years of data collection. But I won't dwell on this a lot. I want to focus on the positives here. So we had to make this manageable, we had to screen the data a little bit. So we made the big decision early on to focus mostly on piped watersheds. There's a lot of open channel and ditch data out there. We would love to analyze that sometime, maybe in a future project, but to keep this simple, we focused on the piped watersheds, and we tried to include as much data as possible in that. So we looked at grab and composite data, base flow, storm flow, seasonal and annual monitoring programs. Basically, the only thing we excluded were, like I said, open channels, BMP outlets, illicit discharge samples, things that didn't have a very distinct, or didn't likely have a very distinct watershed signature. And then we also removed any sites that the agencies shared with us, concerns about data quality or connectivity issues with pumped inflows, things like that. This is really getting into the weeds here, but we did do some QA/QC on this. Luckily, a lot of the agencies are using the Met Council Environmental Services Laboratory, so we at least know the analytical methods are pretty consistent. And then the other labs across the cities are also using similar methods. So we could at least be pretty confident that the analytical methods for processing the samples are pretty consistent. We did some outlier screening. We didn't throw out that many samples. We did find one TSS sample of 200,000 milligrams per liter. So we did remove that one. And anything like that just really made analysis difficult. But again, that's in the report, which you'll be able to find eventually. And then we also had some calculated quantities, organic nitrogen, total nitrogen, things like that. And then for the summary and analysis of this data, we kind of followed the guidance of the USGS using Housel's statistics for censored environmental data and the NADA for our package. We focused mainly on the May to October storm flow data set because that's where the bulk of the data came from. And so we have a lot of summaries included. We kind of sliced and diced the data different ways. We'll show some of this today. A lot of it's in the report. And then we did some detailed analyses with regression, and I'm looking at some of these time series, but really just scratching the surface of what's there. We also had a lot of supporting data. We wanted to develop some watershed characteristics from spatial data analysis. This is to help inform the spatial variability and the nutrient and pollutant concentrations, understand the drivers, and then eventually get to predicting stormwater constituents. We had a lot of help here from Mary Merrick Sparts, especially to develop some of these composite land cover types like street canopy fraction or lawn cover, or watershed age or parcel age, which you can see in this map here. This isn't a complete list of characteristics, but kind of our usual cast of characters are there. Land use, land cover, soil characteristics, population density, that kind of thing. Anything that would be expected to have an effect on stormwater. So the final data set looks something like this. We whittled it down to a mere 91 sites located across the metro here. Pretty good coverage from northwest to southeast, but a lot of the sites located kind of here in the urban core. We ended up with somewhere around 14,500 samples in this data set, roughly, up to 20, maybe even more parameters measured in each of these samples. This top graph, I know it's gonna be hard for you to see, but this is kind of the timeline, number of sites per year going back to 1995. You can see data collection really picks up in 2000, 2005. I think that's coincident with monitoring to support MS4 permits. But as you can see, it's really just accelerating over time. So there's a lot of work going into this. And the only reason it drops off in 2021 and 22 is just because we didn't have time to go back and reconnect with people who'd provided us with data in 2020. So it's 650, more than that, site years worth of data in here. Of those 91 sites, 23 had year-round monitoring. But as you can see in this plot in the bottom right, this is just sample counts by month. The blue color is the storm flow samples. You can see that the bulk of the monitoring is occurring in that May to October period, and it's primarily stormwater samples, which are, I think, roughly about 80% composite samples, the rest being grab sampling. So that's why we chose to kind of focus on that period. But They have a pretty good distribution. We also had some sites with some incredibly long records, 15 to 20 years for some of these sites, which is really incredible for stormwater monitoring like this. So in terms of what's in our final data set, I guess the curated data, the stuff that we really focused on, it's included in the summaries, includes kind of our usual suspects, metals, inorganic nitrogen, phosphorus, TSS, chloride, which is being explored in a current project, so we won't talk much about chloride today, and sort of organic matter, COD, BOD, VSS. And then we have some other parameters that were maybe less better characterized. Some of them are in the database, but not really summarized. That includes a lot of the volume, discharge, and load data, unfortunately. If the concentration data came in a lot of forms, volume and discharge and load information was all over the map. But we would love, there's a lot of information to be gained from that, and we have some information there, but analyzing that just became beyond scope for this project. So in terms of where you can find this, the final report will be available in the next month or so at this address. It'll include a lot of things that we're not going to cover today. And then in terms of the raw data, watershed characteristics, we would like to make this available, but we will not do so without the blessing of the people who provided us the data in the first place. So we're in the process of starting to reach out to people and see what they're comfortable with sharing. And we will try to make that available in some form in conjunction with this report. Okay, so now the fun stuff. So what does this data look like? So the first thing I did was just compare this to what was in the Minnesota Stormwater Manual. So those are the values on the right here. This is for TP, TSS. These are concentrations for residential and mixed land use categories. These are the most common land use categories. The values that we found in our project, slightly higher and a little more variable than what was in the Minnesota Stormwater Manual, but probably nothing to be concerned about, just something to maybe look at with a little more scrutiny down the road. But basically, I think it means that Minnesota Stormwater is, or at least what we found is, it's pretty consistent with what was coming out of the NSQD. Showing some examples here. These are just distributions of site means for phosphorus, TSS, and lead on the right, just to show that we have a pretty good range in variability and pretty even variability in some of these parameters. Certainly some high values if we're looking at TSS. This doesn't include that one astronomical number. We did throw that one out. But one feature to point out here in the TP data, for example, is that if we look at residential land use, it kind of brackets the whole distribution, meaning that if we're trying to characterize phosphorus based on a broad land use category, this is going to be a poor predictor, just that land use category. And then just one note about lead, there's no such thing as a safe level of lead. Most of these site concentrations are above what the EPA considers an action level for drinking water. Not that we're drinking lead, but this does suggest that we have still some lead pollution in the environment, which Jacques will talk about in a few minutes. This being Minnesota, we also have a very distinct seasonality to our stormwater concentrations. This is TP, TKN in the middle, and COD on the right. And these are just the monthly mean and spread in the data. So you can see so we have higher concentrations in the winter, which you might expect. Volumes are a little bit lower, so things aren't being diluted as much. We also see an increase in the fall in nitrogen and phosphorus, and that's associated with leaf litter. And these high and that leaf litter is decomposing over the winter, and that's also contributing to these higher concentrations. And I'll talk more about this in a few minutes. And if you really squint at this, you can see kind of a bump in the nitrogen and the phosphorus, and especially the COD in that kind of late spring, early summer period during leaf out, and maybe while there's some erosion happening from lawns that aren't quite established yet. So we have that to contend with. But if we look at the cold season data, this is the only really bit of this I'll show. I should have put this in a graph, but we see slightly elevated concentrations of most of our constituents in winter relative to the warm season, that May to October period. This is especially true of chloride. That's kind of a no-brainer. That's road salt. But we see this also in ammonium, SRP, zinc, and COD. And that is partly due to that lower volume of runoff. Things are being more diluted in the summer runoff, but we also take this as an indication of decomposition and other things that are happening. And because I couldn't resist, I wanted to put something in here about base flow because this is really interesting, but not something that we really investigated in detail. But base flow is a feature of our larger sites. That's kind of what this plot is showing. So the sites with persistent base flow tended to be larger. And why that's important is because that has an effect on the pathways of different forms of nutrients. And so what this plot is showing is the ratio of storm flow to base flow concentrations. So if you're above this 1.0 line, you're enriched in stormwater relative to base flow. And if you're below this line, it means the base flow concentrations are much higher. So no surprise, chloride and nitrate are much higher in base flow, which is groundwater dominated typically. So that's not really a surprise. Total nitrogen is pretty neutral, but we can see the organic nitrogen tends to be more enriched in storm flow. And then in phosphorus, pretty much everything is more enriched in storm flow, which is kind of consistent with expectations, but it's still always good to see it when it shakes out this way. And then just one more note here on the phosphorus data before I dig into some more detailed analyses. This was something that Mike Trojan had asked for initially, is what percentage of our total phosphorus is dissolved, is in that dissolved form. And what we found is that it's roughly 28% if we just look at the warm season data. If we look at annual, it's about 30%. So most of it's particulate, at least in the stormwater. And in the MPCA MIDS calculator, Mike, correct me if I'm wrong, but TDP is 45%, or soon to be 45% of TP. So this is something that maybe needs a little more investigation, but just something that might be of interest to the audience. And I'll just skip over that. So I wanted to talk. What's that? So I just wanted to talk about tree canopy influences on stormwater. This is something you've heard several of us talk about before. Trees are important for a lot of reasons. So I don't want to sound like I'm harping on trees here, but they also are an important source of nutrients to stormwater. And going back to this seasonality piece, kind of highlighting these times of the year, decomposition of leaf litter and snowmelt. This is total phosphorus again. Leaf out in the spring, and then this leaf drop in the fall. And if we look at this is the soluble reactive phosphorus, this is the dissolve, this is the part that kind of leaches out or decomposes from leaf litter. We can see, if we just kind of fit a smooth line, we can see the leaf drop and the snowmelt in this time series here of all the data points. See the same thing in ammonium. This is, ammonium is something that's pretty rapidly turned to nitrate in warm oxygenated conditions, but over the winter, it does kind of become part of or it decomposes out of the leaf litter and it becomes part of the spring load of nitrogen here, but we see it's pretty low the rest of the year. So if we suspect that the tree canopy is an issue, then we really want to focus on the street tree canopy, or the tree canopy near streets, sorry. So we did this with a GIS overlay analysis. And again, this is where we had help from Mary. So she created a polygon map of all the streets and alleys in the Twin Cities Metro. You can get this map off of Minnesota Geospatial Commons now. We overlay this with canopy data, which comes from Joe Knight's group in the Forest Resources Department here at the U. We can come up with this idea of street canopy fraction. And then we summarize this for all the watersheds where we had monitoring data. Then if we plot that up, we see that there's actually a pretty strong correlation between the street canopy fraction, and this is total phosphorus, or the black points here. Blue is the total dissolved phosphorus. So we can see a pretty good relationship here. This is just the warm season concentrations. If you needed more evidence that leaf litter might be the culprit, we can look at some of our organic matter constituents. This is volatile suspended solids, which has a significant relationship here in the gray. And dissolved organic carbon, we don't have a lot of data there, but it's hard to see because it's on a bad scale here, but that one's also significant with street canopy fraction. So there's a lot of organic matter probably coming from trees that's contributing nutrients. And if we repeat this analysis for the cold season, we see that the relationships actually get a little bit stronger, and that's because the concentrations are going to be much higher, but there's also fewer data points there. But just wanted to mention that. Then also, if we isolate the high canopy sites and look at the seasonality, it's quite a bit more exaggerated compared to the data that I've showed earlier. So pretty good evidence that the street tree canopy is an issue, but we're already thinking about this in terms of street sweeping and things like that to manage trees. So maybe I'm not preaching to the right crowd here. Now, so what will we do with this information then? So this is a map of total phosphorus concentration in the monitored watersheds across the metro. And what you see here, there's a lot of white space. There's a lot of places where we just aren't monitoring. Despite all of the monumental monitoring efforts going on, we still have a lot of blank space here. So is there a place here for doing some modeling of phosphorus? What would that look like? And so just as more of a proof of concept, we did just a quick multiple linear regression analysis, trying to predict this warm season total phosphorus concentration using our watershed characteristics here, our street canopy fraction, but then some other things that we would expect to be related to phosphorus. And when we do that, these are the, I guess, the best models, if you will, kind of ranked by information criteria. And you can see there's some other parameters that show up as being important here: residential area, age, watershed wide canopy. What else we have in here? Single family home lawn. The model with just street canopy is down here at the bottom. So maybe if you squint at this, the adjusted R-squared is a little bit higher. You have a little bit better predictive power using some of these other parameters. But one model I wanted to focus on in particular is this one that has street canopy and population density. The reason I like this model is because we have a mechanism for the nutrient movement. We have a term that describes that. That's the street canopy moving leaves, moving phosphorus from the soil into leaves onto the streets. And we have this population density, which describes the intensity of phosphorus inputs to the landscape in terms of dogs and compost and lawn management activities. So I like this model just as an example to illustrate what we could do. So let's take those two parameters. So we have street canopy fraction mapped across the entire Twin Cities metro here. This has been aggregated by DNR level 9 auto catchments, so we lose some resolution in the urban core, of course, but so we have that. We can overlay population density, which is at the census block level. So those are the two parameters that were in that model. And so we model stormwater phosphorus for the whole Twin Cities metro at block level, or census block level. So this is more just a proof of concept, but this would help. We could throw some other models in here, blend models together to try to identify some hotspots where we might need to look more closely at street management or street tree management programs. So I just present this as an idea. This is kind of where we were headed, this project originally, but didn't quite get there just because of the piles and piles of data that we found. So anyway, I'm going to stop there, turn it over to Jacques the last little bit.
Thank you, Ben. So Ben has got us sort of up to the first case study that we developed in more detail as part of this project. And for the second case study, I'm going to focus on metals, focusing on lead, but thinking about other metals as well. And as you all know, there are diverse sources of heavy metals in the urban environment: gasoline, paint, aviation fuel, lawn products, cars, atmospheric deposition. We know that we've done a good job in terms of driving a lot of these sources of metals down. So emissions of metals in urban environments are lower than they used to be by quite a large margin. We haven't gotten rid of all of the sources, but we've certainly reduced them substantially. We're faced with the legacy of a past of much higher emissions accumulation from some of these sources. So one prediction that we could make and look at in this data set, sort of with those relatively long time series that we have, is that metal should be declining in stormwater. And indeed, when we look at the data sort of in aggregate, all data, we see decline in metal concentrations. This example for lead, and a fun surprise here is data from Brezonic and Stadelman, 2000, which Teresa sent to me, found the spreadsheet, and here it is. So thank you to Pat and Teresa for that. What you can see in this figure, again, this is all of the data. So there are around 8,000 events here represented approximately. We can see here the 1980 USGS study when lead use in fuel was about half of its historical high. So there was still some leaded fuel in the environment, quite substantially so. And you can see that here. And then followed by sort of a decline until lead was banned in gasoline in the 1980s, 1990s completely. And then a long period of a lot of variability and some lead persisting in the environment. So when we look at all of this data, what can we, in the more recent period of this sort of dense data collection, what can we pull out of this? So this is sort of the next part of the talk is going to focus on that question. And the first thing that I'm going to do is to take some information from the park board. So these are just fantastic sites, as well as South Washington Watershed District. That's the suburban site. Minneapolis sites are here. This monitoring, unfortunately, mostly ended for these sites in 2019. It's a tremendous time series data set here. And what you can see is a strong decline again in lead, but a lot of site-to-site variation within Minneapolis for different land uses. So we've got a park, an industrial site, a mixed land use, and a residential site as really sort of showing up as important and much higher source of stormwater lead. When we take all of the data we had across all sites, take a mean for the last decade approximately, and analyze that in terms of an average total lead concentration, and begin to look at some of the things that might make a difference, we can see that one of the biggest sort of predictors of lead is the mean building age in that watershed. So taking some of the data that Ben described earlier, and analyzing it with lead in stormwater, we can see this strong decline in stormwater looking across these watersheds, with watersheds with young buildings showing very low lead or much lower lead concentrations compared to these older buildings, with a lot of variation in there, right? So there's a lot of data that's gone into each of these points. There's still substantial variation within that. One thing that we can say then is that age and heavy metals are related. And if you do a Google search, it's surprising what you find out there in terms of information relating age to heavy metal, including effects on humans and otherwise. So what you can see here for some other heavy metals, so zinc, copper, nickel, all showing declines, as well as the lead plot that I showed you already with mean building age. So we've got a sort of pretty good clue, a lot of variation within these, that the age of the landscape or the building in particular is giving us a good indication of how much metals are active in the environment, or at least ending up in stormwater. So stormwater then provides an indicator of environmental exposure to lead. So it's an indicator of lead that's mobile in the environment, that's moving around. We can map this just like we did for phosphorus and see hotspots in red shown here. These are the high concentration, older building age, older parts of the city showing up here. In the periphery, the suburban areas have much, much lower concentrations of lead. And we're beginning to see relationships among these data and other data sets that are being collected for soils, plants, animals, and even humans. So this is a map of childhood blood levels for the Twin Cities. Same thing in other cities. Again, you see the older parts of cities showing up in terms of still having elevated blood levels of lead in the older parts of our cities, which is a problem. We know that there's no safe level of lead for kids or ecosystems. So we're continuing work to try to understand this. We're seeing, suggestion that paint in particular may be a really important source of lead that is lingering and active, but there's a lot still that we don't understand. So this is really ongoing work and to some extent preliminary analysis in terms of what I'm showing you from here on. One preliminary plot that we've just produced recently is merging data for soils, for watersheds where there are a high density of measurements, so over 150 soil samples. If we have watersheds with a lot of data, we can get a relationship that looks like this. If we include sites with less data, that say 50 measurements, we just see a whole lot of noise, right? So we need a lot of data to establish this relationship. Fortunately, there's more information out there where we should be able to improve on this. But there is a relationship between soils and what we see in runoff, and that is useful. And there's a relationship with impervious cover and lead concentrations too. So I fit a line here. This is showing this interesting relationship between these two variables. We know at low impervious cover, we're dealing with younger landscapes. For high impervious cover, we're in the older parts of the city. We need to understand the history of redevelopment and building type at this high end, and that's something that we would like to do and are looking for ways to do. So much like Ben described earlier for phosphorus, but not as advanced by any means. This is a work in progress, but I think is within reach in terms of developing relationships to map and model lead concentrations in stormwater across the cities. And this is sort of use in terms of thinking about managing construction sites, keeping newly exposed sources of lead in soils from getting into stormwater, and managing BMP. So this is a blank spot, but somewhere that we would like to go in the future. So that's been a lot of information for you, and hopefully you are all intrigued enough to sort of get into the report and read it and make use of this data. So we want to make this information available. There's tons to do and lots of opportunities to do more with this huge data set. What I want to do for the last part of this talk, as we sort of near the end, is to describe some ongoing work, which I've already started to do, student research support. So there have been 5 student projects, undergraduate and graduate projects, that have benefited from earlier versions of this data set. And I think there are just tons of possibilities for projects to do more with this data. Continuing integration with the Minnesota Stormwater Manual. So we started this with Mike, looking at you, Paula. There's certainly, I think, more information that could be integrated here. We'd love to help do that. Interactions with the LTR have been useful. Lots going on there. Ben and I have a chloride project, so we'll hear more about sort of that aspect of the project in the future. And Emily Snellrud, my colleague in my home department, is leading a project on lead bioavailability and remediation. So that project is leveraged by this project and is ongoing. Some thoughts about some near-term opportunities that exist, and there are many opportunities to think about things like BOD, COD, and fog, which were things that I hadn't really thought a lot about in my past, but there's a lot of information there, right? And we should make use of it and try to understand it. So there's definitely opportunities. Hydrology and loading. There's more to do here for sure. This is a tough problem, but I know, with this community here, we can make progress on it. We can enhance the database. I think we've done some of this, but there's lots more to do to look at climate sensitivity, influences of management, like street sweeping in some of these watersheds, keeping track of street sweeping frequency in relationship to event concentrations of phosphorus, for example. Long-term changes, so we've got these 23 sites with long time series. There's more to be done there in terms of thinking about temporal changes with environmental change and management, and leveraging other data sources. So I mentioned this soil database that Nick Jelinski and others are working on for lead. Also a lot of phosphorus information in there as well to bring to the table. So finally, I want to sort of humbly offer some suggestions. So the question marks here are reflective of that for each of these, of things that we might do in the future to continue, enhance this data synthesis activity, right? So first, let's keep this going, right? We've got this database. Let's maintain it, enhance it. It doesn't need to be us by any means, but I think it should be done. So I'll offer that as something that something to consider. Opportunities to do more, coordinate data collection across sites. This is something that's not easy. Everyone has got their own thing going on, but a little bit of planning might help us sort of coordinate our monitoring in more efficient ways. Standardizing data formats could be helpful to solving some of the issues that we encountered, and then integrating new tools, right? So the default explanation here is AI, right? So there are a lot of new tools, including some that are just becoming used in stormwater and water management that we could bring to bear in this. Ben mentioned just the bigger opportunity. So if there's a lot of stormwater data, there's more stream data. Trust me. I mean, Richard's nodding. There's a lot, and we could learn from it. And in the future by bringing it together. Same, I think a little less so, but still there's a lot of information that you've all collected on BMP performance. So we looked at the inflows to some BMPs in this data set, but we didn't do anything with what those BMPs were doing. And in some cases, these BMPs were monitored. The data that we used came from measurements of BMP performance. So we didn't touch that, but someone should go there. We should do this, okay? So I think I'll leave it there for now and say thanks for listening, and look forward to discussion now and in the future.
Thank you both. So we have time for some questions and answers from to Ben and Jacques, from both those online and in the room here. So for those online, you can submit your questions in the Q&A and also vote those up. And for those of you in the room, if you want to ask a question, raise your hand. I want to bring the mic to you so everyone can hear online. So I see one hand up over here.
Thanks, Ben and Jacques. Looking at the high concentrations of nutrients in the late winter, early spring melt, there may be more sources for that, but I'm thinking of two that might be particularly important. One would be runoff off of frozen lawns, and the other would be near street sources that maybe are residual from the previous fall. Do you have an idea which of those is more important? Are they both important? I think it has significant implications for management if we take a look at that.
Thanks for that question, Mike. I would say that the short answer is we don't have a great understanding yet of which of those two things are more important. I think they're likely both important, different times, different places, but we need more information, and it's a difficult time of year to work in to see what's happening, but I think it's worth doing given what we're seeing in the data. Anything?
Yeah, I don't have much to add to that except that, you know, anyone who's walked their dog in the spring also understands there might be some other overwinter sources of nutrients too, and that's also one that's completely unstudied, you know, aside from the leaf litter.
We have a question online. This question comes from Ali. How did you partition runoff into base flow, storm flow, etc.? And how would you explain the considerable base flow from pipes with no or minimal interaction with groundwater?
So that's a good question. We primarily relied on the contributing agencies to make that designation. So if they classified the sample as base flow, we said it was base flow. They all have different ways of doing that. That's one reason why we'd like to go back and revisit some of this data so we could maybe apply the same base flow separation techniques to all of the data and be more consistent potentially. But so we relied on the agencies for that. I know there are probably some sites that have quite a bit of base flow without having groundwater. Those are probably connected to lakes, wetlands, and probably upstream surface water sources. And I think that's something that you could probably infer. We tried to in a previous project just from looking at some of the chemistry data, nitrate or O18 or chloride potentially, which is a really good indicator for, at least in the summer, for groundwater.
All right, we'll take another question from the room.
Yeah, I really liked how you integrated some of the data from the canopy cover. Is it possible to get some of the other watershed or subwatershed fingerprint associated with that data? I'm thinking about like the slopes in a subwatershed leading to a collection point, the different types of soils that are in that, see if there's relationships there. And then how much subscription rate you have in terms of irrigation systems. I think those might all be signals that we could potentially pull up.
Yeah, for those first two, for the slope and soil type, those did go into the regression analyses. That's also in the report, but we had to leave out a few things. So we did look at slope and erodibility, you know, the parameter that's in the universal soil loss equation. Those are kind of poorly mapped in the urban, like really urban areas. So it didn't really turn out to be a great indicator. Slope also didn't have as much, wasn't a great indicator either, but it had some relationships with some of the parameters. I just can't remember off the top of my head. And then some of those other like anthropogenic things like the irrigation and I don't know, maybe lawn care activities could also be interesting. We might need a social scientist for that.
I'll just add a little bit. I think that's what makes this database unique, other than its size, which is it's large, right? It's bigger than the National Stormwater Database, I think, in terms of number of events. It's on the same scale, but it's all in a sort of one location with a lot of supporting information about the watershed characteristics that Ben and Mary have put together. So that's, I think, a really good thing. There are more things to add for sure, and management and other factors. So, yeah.
We have another question online. This actually relates on what you just said, Jacques. It comes from Paul, and the question is, could this data be added to the International Stormwater BMP database?
I think it could and it should. And I think one thing that you see is that there is, there's a lot of data that's collected here in Minnesota. You all know that, and it's not well represented in some of these other databases, the BMP database. So I think it could and should.
And we'll take another question here from the room.
So I've got a list of 10 huge questions. I know, but I have to start with a dumb one, which is you're listing an amazing email address on here.
I don't think that's real.
Okay,
I wish it was.
that's encouraging.
That would be so much easier to provide to people. I'm the original B, you all.
Had to ask. So you're looking kind of at the top of the system, right? You're looking at the stormwater flows. What I'm kind of curious, and there's two aspects to this, which is there useful information to be gleaned by integrating with what you have seen and found at the top of the system with the other end of the system, or the receiving waters in particular? So we got lots of data. You mentioned streams. We got tons of data on lakes. The other one that's interesting, I think, is Capital Region Watershed District, for instance, has a whole data set on their huge interceptors, which would be really interesting to compare with what you're seeing at the top of the system. The other piece to this, in my mind, is when the constitutional amendment money came online, the PCA started just immense monitoring program of particularly lakes all around the state, which I've always thought has to be a data set that is just spectacular on a planetary scale by now. And yet, to the best of my knowledge, nobody's done, it's wonderful that this work was done. How wise of the Research Council to see that it was funded. But something similar, it seems, should happen with this immense data set that the PCA now has.
Yeah.
Thanks.
Jacques, I'll hold your drink. Do you want to answer that one?
Yeah, thanks for that question, Randy. Absolutely. I mean, I think Como Lake here, getting a lot of stormwater. We know a lot about that stormwater. We know a lot about the lake that's put those things together, for sure. Absolutely. One thing to say is that those big drains for Cap region are in the database. You can look at watershed size. That's sort of all part of this really diverse data set. So there are some enormous drains in there and teeny tiny watersheds and everything in between. So, yeah.
And I thought you were going to mention the fact that there is a whole contingent of people within the LTER who are trying to gather up all that lake data within the Twin Cities and look at it. And we're trying to look at a subset of that within the chloride project to look at stormwater in these drains and how that compares to trends in the lakes and streams, because we have really good data there for all of that.
I would say trying is the word. And, I think this is it's a huge challenge and undertaking. So I think, the more people that are involved in this, the better.
We have another question online, and we actually have a couple questions related to this. Did you try to model pollutant loads? It might make the seasonality a little clearer and management more understandable.
I wish. We were surprised, I was surprised by how much hydrology data, at least that we were aware of, that was being done. A lot of the stormwater monitoring has to be done with, you have to collect flow data to know how to time the samples. So there is a lot of flow data, but in some cases, it's just in all different forms. It would be another project to do that, but it'd be super cool if you had like the same load calculation being done for all of these different data sets. And then you could get at that seasonality question, because we have really high concentrations because the volumes are kind of low, although we're starting to have more December thunderstorms and things like that. So maybe that's, anyway, yeah, but I wish. In another project.
So there is loading calculations done by individual organizations to sort of standardize, harmonize those things. We ran out of gas in terms of getting that done. I mean, it's requires a lot of hands-on work that maybe there are better ways to go about it, but we sort of ran into just the diversity of data formats and the cleaning of the data to get it into shape was a challenge.
Yeah, and some of the groups are doing a really good job with their load calculations. I should say that. I don't want to paint with broad strokes there. Everyone just has different budgets and time constraints.
But doing it all the same way
would, yeah.
yeah,
It's
Yep.
beyond us.
Well, that's just great. We are going to continue our question and answers, but we're going to add a few people to the discussion here. So first of all, a round of applause for Ben and Jacques. And I'd like to introduce a panel of local organizations and representatives that have contributed to data that have gone into this project to join Ben and Jacques for some additional Q&A here. So if our panelists can come on down, and Jacques and Ben, if you can have a seat at the hot table here with our other colleagues. And go ahead and continue to provide your questions online, and we will have time to address some of those from you online as well as here in the room. So we've invited a few panelists to join, and we have some questions about their contributions and use of this work. And so I'm going to start on my far right-hand side, your left, with our first panelist, Richard Kiesling from the USGS. Dr. Kiesling is a hydrologist and a limnologist with the USGS and has done a fair amount of monitoring and work with data. Richard, from your perspective and experience, how do you relate to this topic and the use of this work?
Well, thank you, John. John asked us to think about how this work might influence the issues for our own work, thinking about the advantages of the data compilation, first of all, and secondly, looking at those trend relationships. And just to play off some of the questions that were already stated and thoughts I had while seeing the presentation is the relationship between total phosphorus concentrations and the seasonality in leaf production and the base flow production. The best of those regressions explained about 36 to 40% of the variability in observed variability in total phosphorus load. So the question that comes out of the data set really is, where's the rest of that phosphorus coming from? The other thing I always like to bring up when we talk about trees and the nasty role they play in giving us particulate phosphorus is, where are the trees getting that phosphorus in the spring? And I think these large databases maybe give us an opportunity to think about closing the loop on budgets for these pollutants that we're interested in, phosphorus, nitrogen, on some of these urban watersheds where we've had extensive monitoring. But the point that I'd really like to bring up is that the advantage of this kind of data compilation allows us to do the kind of vulnerability index calculation or development that Ben and Jacques have shown us today, using advanced regression methods. And I think that's pretty exciting because they've only really scratched the surface. And again, I was thinking about the lead model, for example, adding trunk highway miles, because those trunk highways, I live in Roseville, Minnesota, and there's County Road C, and County Road C was carrying traffic a long time before Roseville built up around it. It was farmland, but I'm assuming there's a gradient of lead concentration moving away from that major county road and from the trunk highways. So those are the kinds of variables that can be added or tested in this model. And of course, I haven't seen everything they tested, so it might already be in there. But my focus is about receiving waters. And so playing off the question that was asked about how we tie this to other kinds of monitoring data we have, I think we can use this as a way to highlight places where we can focus in on receiving waters that are at most risk for receiving these inputs, maybe understand how they're responding and how we can manage those receiving waters as well with this just exciting large amount of data that's available to analyze. So I'll stop there and let my other panelists chime in.
Thank you, Richard. Our next panelist seated to Richard's left, your right, would be Shahram Missaghi, and he joins us as the Water Resource Regulatory Coordinator for the City of Minneapolis Public Works from the Surface Water and Sewers Division. Shahram, you've done a fair amount of monitoring and you've contributed data as your organization, your city, to this project. What is your perspective and experience related to what they've discovered?
Sure. First of all, thank you, John, and thanks to Jacques and Ben for doing the work and your presentation. Really exciting. And how I relate to work like this is, as was mentioned, I work in the regulatory team, and I'm responsible for managing and implementing stormwater plans or stormwater management. And I guess I would relate to this data compilation in three ways, maybe. One would be regulatory compliance. Very interested to know where our stormwater practices or the watershed it's behaving, or where the stormwater practices are failing, just to know where and when, both the spatial and temporal, where are they, what's happening, are they filtering, are they adding? Those would be very important for us. And also knowing why and how they fail. The other part would be benchmarking, and which is much of what this project has done, is to establish a benchmark to know what is the information, what data do we have, and having clean data. In our work, we do a lot of monitoring of the best management practices to understand if they're functioning as they were designed, and why are they again failing, and understanding and being able to analyze the data. And hopefully by analyzing data, as many of the plots you showed, being able to find a trend and understanding, well, what's happening, and using those trends to kind of to do what you were mentioning. What are we doing with our local water resources, to our lakes? Because ultimately those are what our goal is, to have clean water. And hopefully having the trend will help us to do modeling, which again, helping us to manage really manage the future. And I know one of the things I picked out from your abstract when your presentation was to having the ability to reveal relationships with key urban land cover and climate variables. I think that would be the key. That would be amazing. Thank you, Shahram.
And our third panelist joining us this afternoon is Emily Resseger. She's the Monitoring, Assessment, and Research Coordinator at the Mississippi Watershed Management Organization, also a sponsor of the Minnesota Stormwater Research Council. But previously, Emily was also with the Met Council, our regional planning authority that does a lot of monitoring as well. So from the roles that you fulfill, Emily, what's your perspective and experience about how this work can be used?
Thank you, John, and thank you for including me on this panel. Like John said, I've recently switched roles. I was at the Metropolitan Council, which for those of you listening from outside the region is the regional government agency here in the Twin Cities. And when I was working at the Met Council, I was especially interested, like Richard and Shahram mentioned, in surface water issues. So assessing the quality of Twin Cities rivers, lakes, and streams, especially looking for long-term trends and understanding the relative load contributions from different parts of the metro for a lot of pollutants of concern. And all of that work, one of the main goals of that was to inform local planning efforts and to set regional water quality goals for the region. And so, this work I think can be directly used from a regional perspective on looking at what pollutants do we really need to be prioritizing, especially some of those heavy metals may have sort of dropped from a lot of the regional conversation, but I think there's a need to maybe be re-examining that again. So I think this can help elevate pollutants, and then also be thinking about what kinds of stormwater practices should we be encouraging around the region that will best target the pollutant levels we're seeing. And I think that that will end up having the biggest impact on the waters of the region, which is a lot of the goal of what the Met Council is doing. At the Mississippi Watershed Management Organization, which is a more local scale, like I know Shahram here, we're one of the organizations who contributed data. So as a data geek, we always love to see people using our data other than ourselves. So it's really exciting to see our data being leveraged. But I think this is an opportunity for us to see what some of our peer organizations are doing. We can't monitor everywhere in our watershed. And so we're trying to understand from the parts of our watershed we do monitor, what insights we can learn on other landscapes similar to ours. So that's something I'm hoping to be able to dive in to what you're doing. Personally, for both of my positions, I've been very involved in data management. So I deeply feel Ben's pain in the 2 years he spent with corralling data.
Well, thank you all. And so we're going to use the next half hour or so to take questions from the audience, both in the room here and online. So please submit your questions. We do have a couple questions that we'd like to ask any and all the panelists to respond to. I'm gonna skip to a question here. Ben, as you said, enriched winter contributions, I wrote as a sub quote. So my question to any of you is, we might be missing out by having valuable data not collected year round. So what are the specific challenges around year-round monitoring, especially for those here in the upper Midwest, and how might we overcome that challenge? Any of you?
I guess I could start. My new organization, I'm much more involved in the monitoring, and we're just starting to winterize and remove our equipment as we always do. And I think one of the things we need to do is just reevaluate and prioritize winter monitoring on its own, not just continuing our summer and good weather season monitoring and sort of making do. I think we always remove a lot of equipment out of fear it's going to freeze. I think we need to be weighing what equipment is a little bit more robust, prioritizing that, thinking about how often our equipment really does freeze. We do a lot of winterization, and then you sort of have to, in the spring, come on unwinterize, and often by that we miss the first or one or two big melts. So I think we need to be thinking about how do we set up our winter equipment in a way that it can, get going right away in the spring. And then, I think there are those safety challenges that I think Jacques mentioned, and we just need to be especially careful of those. I agree with folks who said, we need to be looking at winter loads and understanding how much we are seeing actual higher load contributions. But regardless, we don't have a good handle on it. I think you had a lot less winter samples as well. So I think we need to just be doing a better job of getting out there. And, we're starting to think about how do we do site design for chloride in the winter, not just in the summer. And so I think we need to be thinking about monitoring the same way. How do we optimize it for the winter?
And I would add, having done winter monitoring both for a chloride project, and then also Cap Region was kind enough to help us instrument a very small residential site for a couple winters. And they definitely lost some equipment in that process, I think, when things froze. But we got some very valuable data out of that, and maybe it's something you don't need to do every winter. But we were in that project, we were able to kind of rough out an annual phosphorus budget and found that about half of it came through between November and March at that particular site, which was huge. But I know it's also really complicated because any site that's close to the surface or has exposure to the air, by spring, you're just getting freeze thaw. And if you don't babysit that equipment, and even if you do, it sometimes fails. So it sounds like, Emily, you've got some good ideas, but I have sympathy for the people who are trying to do this work.
Just add a little bit to that in terms of the variability. The year-to-year variability is huge, right? And so we have some years we have a lot of overland flow and some with very little. And freeze thaw melt events, I think, are increasing. And so I think this issue isn't going to go away, but it's going to be one that is just hard to deal with the variability that's out there. So we just have to be, realistic and put resources into it to get better data.
I think I would add that we didn't talk too much or hear too much today about trace organic pollutant monitoring, although the slides did mention CECs or contaminants of emerging concern. The work that we've done on CECs, sampling seasonal runoff, catching snow melt, has shown that that's actually when we see peaks of those trace organics as well. That it's not surprising that they're accumulating over the winter, and that with snow melt, especially when we have those February or March thaws that might be associated with rainfall or some other kind of fast melt situation, we see very large peaks in concentrations of individual compounds and in the number of emerging contaminant compounds that we're detecting. So that's just an added complexity on top of the other issues of trying to monitor phosphorus and nitrogen and other more conventional constituents around the year.
I just like to say, yes, we're missing a great deal by missing the winter. As it was well said by everyone, I think the analogy that I use, let's see how well it works, is like stand in front of a window, you look outside and you get interested looking at the birds and the people and the cars, and you say, let me study it. And somebody pulls the curtain and you go away and you wait for the curtain to open up, you come back and you say, okay, let me see what they were doing. And then it happens like 20 times. And that's how it is with our winter. We sort of shut down and we pick up in the spring thinking we're going to follow this story. And I think we're missing much story, what's happening in the winter. And fortunately, we have tools. I think we can do it. I think equipment has improved. We also have modelings that we can not to take over for monitoring, but it can help us to do better job in monitoring. So yes, we are missing much of the story during the winter.
Well, thank you all. And so what questions do you have in the audience, either in person or online, about this story and data use?
Thank you. This has been great. My question is really about the sampling methods, I guess. And I'm curious if the database recorded kind of a automated sampler versus grab sampler. What was the variety of sampling methods, and how do you think those sampling methods, as Shahram just said, there's a lot of tools, how can that be standardized, or what are your thoughts on the tools we should be using, or kind of moving forward? What do we need to see on those tools?
I just wanted to, well, first I'll try to answer your question, and that most of it is sort of standard ISCO sampling, and base flow sampling was very often grab samples, and occasionally we included some stormwater grab samples as well when they were when there was enough of it. So if we exceeded a threshold, then we included those grab samples as well. But the vast majority of information is coming from ISCO sampling. And I'm going to take this opportunity to put a plug in for your seminar in January. So hearing about the chunky stuff, if you want to hear about all of the things that we're missing in sort of sampling that way, John's going to be presenting on that project in January. Can't remember the date, but I actually wanted to mention that in the seminar and forgot. But yeah, we're definitely not getting the gross solids in this database by and large.
Way to turn the question back to the person who submitted it. Can we take a question from online?
Questions online, yes. We actually have two questions related to sediment. And one is a lingering question from Jacques and Ben's presentation, but another relates to the panel, and I'd actually interested in what the panel would like to say to this. Questions on sediment. First, do we have information on particle size distribution in stormwater runoff for out of these studies? And then secondly, more specifically related to building age versus concentration of nutrients or sediment, TSS, things like that, and thinking about impervious and BMPs, because sediment obviously is captured differently than dissolved.
I'll dive into that one. And I might need a reminder of all that's there, but I would say where to start. One issue that we face is, and I think this is something to talk about more. We see some outliers in the data set with sediment. We see some, Ben mentioned the 200,000 milligram sample. That's extreme, but there were some other ones that really got up there. And the organizations sort of had their own, that we got the data from, had their own QA/QC process, and these samples went through that. And we don't have any way of knowing necessarily, is this a real data point, or is it, equipment error, something that shouldn't have happened. So that is in there in this data set, some mysteries and some real extreme outliers. And we didn't remove them for the most part, except for a few. So those points are still in there, and we could definitely go in there and look at what happened in terms of the rainfall intensity. Communicating with the people that collected the information and getting those notes, I think could be really valuable. One thing to say, there are some surprisingly high TSS numbers in places that we wouldn't expect them. And I think this is part of the lead story. Some redeveloped areas, recently redeveloped areas. This is speculative, but you know, there is a legacy of construction and renewal, which is, I think, helpful for you know, stormwater infrastructure, but also stirs things up a little bit. So more to say on that in the future, I hope. And then in terms of particle size, there's not much in there, but there is some information. So City of St. Paul has included in the past some information on particle size separations, but very little really in terms of the much larger data set. So there's a little bit, and we can call out what we know from the data set, but there's not too much there.
Yeah, I can just add that you know, that building age or parcel age did end up in kind of in the hopper in the regression analyses, and I covered a lot of that really quickly, but some of those other models that showed up in the multivariate analysis did have age in there paired with, say, residential land use or with watershed canopy. So that suggests that you know, that there is an effect of older environments, older residential environments might have more phosphorus, and some of that could be legacy. Phosphorus might have nothing to do with trees. You know, it might be a legacy of something else too.
Great. So let's take a question here from the room.
So as long as we're talking about particle size, maybe you could use this report to suggest that we start measuring particle size, because there are techniques out there that use lasers and things like that to measure particle size, and they're actually fairly effective. You have to pay for the equipment, and so you'd be measured. But most of these samples are sent off to, for example, Met Council, right? Met Council could purchase that equipment. I believe they can afford it. But my question is with regard to base flow. I noticed you were comparing base flow to things like dissolved phosphorus concentration. And it's assumed generally that only chloride and nitrates go through to the receiving waters, but not phosphorus or metals or things like that. And so my question is, what did you find with regard to the base flow concentrations of phosphorus or metals or anything like that, that we are assuming disappears once we infiltrate it into the ground?
Well, it's non-zero. I can tell you that. So I didn't actually plot so they showed a plot with the ratio of the storm flow to base flow concentrations, and since those weren't, you know, infinite on the stormwater side, there is some dissolved phosphorus that shows up in base flow. It's just at a much lower, you know, it's much lower proportion of phosphorus than it is in storm flow. And I don't remember what the metals look like actually in that regard. So I'll have to get back to you on that one.
They're low, much lower overall, but I'm remembering a little bit of, again, some preliminary plots that we worked on this summer, showing, you know, the number of surface water connected water bodies or surface water bodies in a watershed seem to be making a difference to something that we were looking at.
Chloride.
Chloride for
Yeah.
sure, but some other things too. And I think that's what, you know, these watersheds, some of them are they're all runoff from streets, and some of them are actually spilling through catchments, through ponds. I know at MWMO, we had a fun field trip there a few years ago when we sort of looked into the vault at the stormwater research facility, and we saw lots and lots of duckweed floating down in this dark chambers that had come from upstream from some stormwater pond. So yeah, there's some complexities in this watershed for sure that make a difference in these watersheds.
Andy, we see a question online.
I do have a question online. Yep. The next one comes from Mary. What, if any, role did MS4s have in collecting or using this data? And has it been used to support TMDL implementation?
I think, yes, for sure. Because as MS4 and being a regulatory, you need to evaluate the performance of your BMPs. You know, if we're putting a lot of the best management practices or stormwater practices into ground as to help with the situation, to clean up the water. And then we need to monitor these to understand if they're doing what they were supposed to. And also with the TMDL, many areas in many local areas, we implement this or we require development to treat the water to a certain percentage, to a certain degree or a threshold. And those thresholds are set by what we think or what we have monitored the watershed loading to be. So all of this data can inform all those policies. Does that help? Did I answer the question? Others?
We'll take a question here from in the room.
Jacques, since you mentioned that some of the watersheds were full of water bodies and some maybe, cascade through a series of BMPs, I'm just wondering, I suspect you looked at some of that in the report, and I wondered, did you look at all at areas that changed significantly were developed or otherwise transformed over the course of that data set? Seems like that would be really complex to evaluate because you've got changing conditions, but just maybe give us a sense of to what degree you were able to take those land uses and changes into account.
Yeah, thanks for that question. It's a really good one. And I think this is sort of another opportunity. So we did write a proposal to LLRB that was not funded, but I think to do some of that work in terms of trying to reconstruct changes through time in watersheds. So that opportunity is there. And I think for some subset of sites, we could really learn a lot from doing that. I will say Three Rivers, if you're, is one really good example. They have long-term monitoring on some sites that have changed substantially. So transition from unguttered to curb and gutter drainage, and you can see the effect in that data as an example. So I think we can definitely learn more from these time series, and there's not much of that in the report. So don't get your hopes up on that front, but I think that could be done in the near future.
I just wanted to add, it's not an answer to your question, but with Mississippi WMO's data that was used, our watersheds have been fully developed since these monitoring programs began, but they are seeing a decent amount of redevelopment. And I didn't see that as one of your variables, which I think is probably going to be fairly complicated to, you have all this development age, but what happens when a site redevelops? That's something I would like to take back to my organization and start thinking about. It's not something I'd given a lot of thought, and that sort of, piqued my interest.
Yeah, just say we only really scratched the surface of those longer data sets. It just seems a crime to take 15 years of monitoring data and compress it into an event mean concentration. You lose so much information there, but that was kind of how we had to do it as a first cut, and kind of how this information tends to be used. And there's one example that we've shown many times that is in the report of one of the South Washington Watershed District sites, MS1 or MS2, where when they started the monitoring in 2000, it was cornfields and some residential development on a golf course. And now it's like shopping centers and dense residential. And you can see the signature of disturbance in the TP and TSS data early on. You have peaks, and then that kind of levels off. As that levels off, the chloride concentrations start creeping up. And so you can see the whole development picture in 20 years of monitoring. It's fascinating. It's as an illustration. I'm not sure how you turn that into something that you could use or make it more broadly applicable, but that example is in the report.
I think that's an example of a really high value time series that is just amazing. 20 years of data, more than 20 years of data, and the decisions about maintaining it or not. I mean, we don't know a lot about sort of those decisions, and they're made at the local level. But I think keeping some of these time series going. I think clearly South Washington recognizes the value of that and has kept it going. But anything that we as a community can do to, support that, I think, is going to be useful.
Yeah, I was just
Comment on
going to
that?
make a quick observation is that those examples illustrate the power of the database, but the difficulty in capturing all the metadata associated with a site. I'm not even sure I would call that development sequence data metadata, but it's the importance about that particular site. So that's a cautionary tale about using the data out of a database like this without doing the heavy lifting of knowing what's going on at the sites that you're analyzing. So just cautionary tale. USGS deals with that quite often in some of our long-term data sets as things have changed over time on surface water sites and degree of regulation of a stream, for example.
We're going to take one more question here from the room, and then we're going to wrap it up with some final words. And for those of you online, we will save all the questions and present those back to our speakers and panelists for some comment after the seminar today. But for our final question from the room.
Yeah, thanks, panelists. The conversation from earlier about the base flow piece and then the kind of those extreme event outliers in the sediment piece got me thinking about, like, the temporal dynamics here. Base flow feels like it's an easy thing to monitor because it's, low, it's going to fit in our ISCO samplers. But, it's also, we get interflow between water bodies that we're completely missing. So this might be one of Richard's, asterisks to, those system understanding that we're trying to glean from this. And then it doesn't surprise me at all that the sediment outliers could be significant, because that's when sediment's moving really fast. And just, thinking about the flow data that, I know you don't do loads, but the flow data that these were associated with, generally this might be monitoring data and the concentrations that's, the stuff that's easy to get. How much do we underrepresent some of those extreme events in the data? So any cautions or reactions you have kind of thinking about that time element?
Yeah, I completely agree. And I think, really it's a matter of time in terms of limited time for this project for us. But I think for sure we can, someone can get in there and do that work, find that information to understand those important outliers. Are they real signals or are they not? We have some load calculations. We don't have a complete curated data set. So it's not to say that we haven't done any load work. And if you're interested, anyone, we certainly have, or can point to some data sets that I think are in really good shape, and then some places where a lot of work remains. But those opportunities are there, and we just need more people working on it. Again, I mentioned the student opportunities, but other people as well in terms of getting in there and digging into the data set. Yeah. So hopefully we've lowered the barrier to entry in terms of working in this data in this project. That's a big goal, is to sort of provide some foundational support for next steps.
I just want to add that I think we all know in this room that stormwater sampling is really hard, and the technology has not really changed very much in a long time. So we've been sampling, 15, 20 years, we've been sampling these storm events, and, like an individual organization will, put that in their annual report or maybe use it in one TMDL. But like a lot of this data is like just basically goes in a spreadsheet and is forgotten. I think it's really hard to get an entire event. You might, you run out of bottles and then you miss like, the second half of the event, or, something malfunctions. And I think when staff are going out week in and week out and doing this work, and then it sort of goes into a spreadsheet and is lost, you can lose some of the immediacy of like why this matters. And so I think getting these results out and talking about them more, I think can also inspire the staff who are doing this work to understand why this matters and why it really is important that they get their, their trigger elevations set well and their volumes set well, because how is this data going to be used? So something to think about.
Well, great. I'm going to use those comments as a transition here. We are out of time, but I do want to get some final comments from each of our panelist members for key takeaways. So maybe with a minute or less for each of you. I'm going to start with you, Richard. Key takeaways from our possibilities in combining data and using it to our advantage for our work in cities.
Well, I think the thing that's impressed me most is the wealth of data that's available, the importance of this kind of compilation activity. And I think we need to consider applying it, as I think someone in the audience mentioned, to our BMP databases and actually our BMP practices. I know that we've been talking about this. Bill Seelbig, I should say, at USGS has been talking about this kind of compilation on green infrastructure practices and trying to collect additional data on what's working, what's not. So I think that's one of the huge takeaways. The other thing is, just from what Jacques and Ben and others have said, there's a real opportunity here, perhaps by sharing this database with people digging deeper into case histories or specific examples of what's happened over development cycles, for example. So I'll leave it at that.
All right, thank you. May I have two takeaways?
In 1 minute.
1 minute. First, I want to emphasize what Emily said. I think the idea of why we monitor, that would really help us. I think if we talk more about why are we monitoring, what is the stressor we're trying to track, how is that information going to be used, I think it's going to help us to have a uniform result and be able to compare apples with apples. I think that's, as a monitoring person, I guess that's really the thing. Keep asking ourselves, why are we monitoring? What are we going to do with the results? And the other key takeaway for me was that we need the data. I know we still need expertise. We still need experts, our experiences and gut feelings. I think climate change has changed our framework, and what worked before, it's not going to be copied tomorrow. And I think we need data. We need, evidence-driven policies. Thank you.
I'm going to focus my takeaways on data management. It's a passion of mine. I think to be able to keep this work going and have even more data that we can be leveraging, we need to put resources towards this work. There's no shortcut. Shahram and I have both been working over time with a group. I'd encourage folks listening from the Twin Cities to join the Twin Cities Water Monitoring and Data Assessment Group, TCO-MODAG. We're a group that's been meeting for about 5 years with the goal of standardizing monitoring, assessment, data sharing, all of that. And what we found is that the monitoring piece is the easiest one to tackle in our bite-sized events. You can go out and you can learn how to, gauge a stream, or you can go out and learn how to use an ISCO. But, assessment, using the data and then storing the data are more systemic challenges. And they often involve more expertise. So the people who are tasked with that also have like a million other responsibilities. Each organization is different. And so there's not a lot of shortcuts to data sharing. I love the idea of leveraging AI, and I'm really hopeful we can. But there's people out there who want to be doing this work, and there's some of the baseline, already set up in groups like TCO-MODAG, but it's hard to keep them going without a lot of resources, because Ben isn't going to be able to do this forever and do all of it. Even though I hope he can. Thanks.
Key takeaway: Ben's not going to be doing this forever, but I'm sure Ben has some other key takeaways.
Well, I had a hard enough time distilling our work into 40 minutes of slides, so one takeaway is probably a little much. So all I really want to say then is take this opportunity to express my thanks to the MSRC for funding this, to all the people who contributed data, handled many data requests from me. I'm grateful for all of that, for the opportunity to work with this. And going forward, I'd love to continue working at a lot of these things that have been brought up, bringing in climate, land use change, and those really important things to, I'm not out of energy yet. So I'm still excited about it.
Thanks, John. Yeah, I think I just agree with everything that's been said here, and thank you for this opportunity. I mean, it's just been super interesting, and looking forward to taking those next steps, and with the community, and hoping that there's going to be ways to sort of build this in more formally in the future. Clearly, we need that organization in the Stormwater Research Council, in the Water Resources Center, or somewhere here in the state. Thanks.
Well, great. Well, that might be the end of our seminar today, but it's not the end of the conversation. And so I'll look forward to the final report for this project being posted shortly. And please do reach out to us if you have seminar ideas for the future. But at this time, we're going to conclude our seminar with a round of applause to our two guest presenters, Jacques and Ben, and our panelists. Thank you very much for joining us today. And that will conclude our seminar for today. For those of you sticking around for the Stormwater Research Need Focus Groups, we'll take about a 5-minute break and we'll reconvene here in the SAFL room or through the separate Zoom link that's been provided to you online. Thank you for joining.